Here we're going to start looking at a couple more questions to do with E equals mc squared and energy mass conversion questions. One of the key things that's brought in here is that you have to use your tables to find a lot of these figures. So the figures are just there to be looked up, and the main thing is you know that they are in there because they might not tell you in the question that what the figure actually is, so then you got to go use the tables to look that up. So in the previous questions they made life easy and they gave us the figures for each of the masses of the atoms in kilograms, but typically the masses are listed as U, so that's in these unified atomic mass units, just called U. You can find out what this figure is on page 47 in the tables. So for this question 1 on page 370, what you are asked to do is you are asked to calculate the energy in electron volts that is equivalent to 1 U. So we want to figure out that much. So what is 1 U? We need to get it in our SI unit of kilograms. So we just look it up and we find that there. We need to find the energy. So energy E equals mc squared. So we take E is equal to the mass times c squared. So again, I haven't been told what to say c is, so I'm just look up the figure on page 47 in the tables, and that's a more precise figure for the speed of light. So you can see there's 3, 6, 7, 8 decimal places. So I would use this one unless I'm specifically told otherwise. I don't think you can really go wrong by being extra accurate, whereas if you round it off and take 3 by 10 to the 8th, you might be outside the range. I'm a bit inconsistent in some of these questions with my units, but my advice would be just take all the decimal places you can, all the decimal places you're given, and just round off at the very, very end. I don't always do that through the questions, and to be honest, it leaves some more headaches than it would have otherwise, because a lot of the times you just have these figures on your calculator screen, so there's no need to round off because you can just use what's already there. So again, from my tables I can look this up, and I find out that 1 joule is equal, well, not look it up, but I can find out this. So there's my relationship. 1 joule is equal to 1 over 1.6 by 10 to the minus 19 electron volts. So that's back to our previous thing. The charge, the 1 joule, that's all given in the tables as well, so you can look that up. So this is our relationship. 1 joule is equal to this little bit of an electron volt. So I know that's this many joules I'm looking for, so I multiply both sides by 1.4 by 10 to the minus 10 joules. So I come down here, and again that is rounded off, probably rounded off a bit early, but we go through, we multiply both sides, we get this long figure here, that's in electron volts, and they'll always ask me in mega electron volts, so mega is by 10 to the 6th, so move the decimal place 6 places left, and then give whatever figure you have left then with 2 decimal places. So I'd always give the answer in mega electron volts to 2 decimal places. That's typically what they look for, but keep all of the figures before. So again, that figure look up, pop it into that equation, it gets my energy in joules, multiply both sides by this, and I get my energy in electron volts, and then switch it into mega electron volts. That's kind of a bit of an easy one just to go back over what U is and know that you can look up U. Question 2 then, it says calculate the energy in both joules and mega electron volts released in the following reaction. So here we have the radioactive decay of uranium-238, which goes into thorium and helium. So given that the atomic masses of thorium and helium are this, this, and this respectively, so again, that's given in U rather than kilograms. So you can change them at this stage, but if you change them at this stage, you're going to need to do 3 different conversions. So what I did here is I just found the loss in mass and kept that U unit, because I can convert it then. See here, it's gone from U to kilograms in this step, so that just makes life a little bit easier. So keep working with U until you're ready to use the E equals mc squared formula. So again, I find my loss in mass, so that's the mass of the reactants minus the mass of the products. So this one gives out these 2 particles, plus there'll be the extra Q here, the disintegration energy, so that's what I'm trying to find. So that's my loss in mass, so it's lost 4.558 by 10 to the minus 3 U. I change this, so that's my 1 U, back into page 47 of my tables. So I look that up there, I find out what 1 U is, so then I multiply both sides by 4.588 by 10 to the minus 3, and then I get this figure here. So when I round it off, it's 4.567 by 10 to the minus 30 kilograms. I forgot to write the minus 30 in there, so I just wrote that one out. So I did round off going on to the next step, but again, I kind of regretted it. But just keep it at this, 4.568742232 by 10 to the minus 30 kilograms. So again, that's a very, very, very tiny amount of mass that was created by 10 to the minus 30. So that, again, what I'm asked to find, I'm asked to calculate the energy. So I've got my mass, so that's my mass that has been turned into energy. So how much energy will this tiny, tiny fraction of mass give us? So we then use Einstein's equation, E equals mc squared. So that's my mass, which I calculated just a second ago, rounded off a little bit here by 10 to the minus 30, multiplied, I just used 3 by 10 to the 8 meters per second for the speed of light. Why I use that here is in the textbook. Previously, they say in all future questions, take the speed of light equal 3.00 by 10 to the 8 meters per second. So, like I said, a bit inconsistent, but it's a good idea. If you're not told exactly what to make it, just take it from the tables, page 47. That's where all the figures are going to be coming from. So I multiply these two things together, and that gives me my energy in joules. I'm also asked for my energy in mega electron volts. So again, 1 joule is equal to this fraction of an electron volt. Multiplied both sides by the energy you have in joules. And again, you can see I forgot the prefix until I put it back in. So just be careful, watch your P's and Q's on both of these things. Multiply those and I get 4.26 mega electron volts. So again, that is the order you'll be looking for. So if you were like me and you didn't realize you forgot to buy 10 to the minus 13s and you get an enormous answer, kind of be wary. It should be between 1000 and 1 mega electron volts. So 4.26 mega electron volts, that's a pretty standard answer. So that is the kind of final piece to those E equals mc squared puzzles. You will typically be given values in U. You got to convert the U into kilograms, use this equation, find your joules, and then find your electron volts, and finally mega electron volts. So that's your basic beginning stuff, and that's a little bit like what we did previously. The rest of the calculations we have, again, it calls upon some of the stuff from previous chapters. So we'll use the Planck's constant form, Planck's constant, we'll use E equals hf, and a few other things like that. So make sure you get familiar with these. Practice going through them. Just do the same questions I did. If you get stuck, just look through, see what you did wrong and correct it. And if you just get smooth that you can do these questions quickly and efficiently, you'll be in good position going forward. We'll see more examples as well as we go to exam papers. So if you feel like I'm stealing from you, you can go to exam papers and get some practice out of those instead.